So I'm excited to give a talk today. I feel like a lot of the other ones were really nice and detailed. Mine's going to be a bit more of a pitch and an overview of sort of how I think we can incorporate remote sensing a lot more into a lot of these approaches we've been talking about. And I was the one that asked Jared about color. I was thinking about some work that I'll show here where we are using color to sort of inform how we model lakes that we don't have a lot of in situ data. So I'm going to talk about the importance of open access training data for global scale remote sensing of water quality. My name's the only one here, but this is with a huge group, and you'll see names pop up as I talk about specific collaborators and projects. So I hope it's clear from this talk so far that a lot of what is cool and going on in machine learning and AI more generally, not just within the aquatic sciences, requires a lot of data. So this is a really cool little paper I found from a YouTube channel I really like, just showing how they trained a neural net to basically impute sunsets and sunrises on any given static image. And of course, to do this, they had to use videos and images that were in public archives. So they just sort of scraped the web for a bunch of information, and they used 20,000 photos from the internet that were either of sunrise or midday or whatever, and then they built their model based on all this open access data. And I think when you look at traditional development in computer science, the sort of core algorithms are developed on these really radically open public data sets, like photos that you can just scrape off the internet, or other labeled machine learning data sets. And when you think about water quality, there's a bunch of these data sets available. I didn't move my slide early enough, but basically in a bunch of fields, there's tons of these labeled machine learning training data sets. But for remote sensing of water quality, we really haven't had this data as much that is open and labeled and very clear and easy to use. And in this paper by Simon Top, we sort of show that the predictive accuracy of remote sensing models, this is just an R squared, on either the fit of the model or the validation of the model hasn't gotten a ton better in the last several decades. And potentially one of those reasons is that we just don't have large data sets that we can all sort of compare methods across. Traditionally, when doing remote sensing of water quality, people were doing the sort of local study and then doing their validation just on maybe 100 or tens of points actually. And we sort of pitch in this paper that one of that problem of not having an open access data set led to this long period of decades of time in the remote sensing of inland waters, where we were really focused on two types of analysis in our papers. One was methods with a slight description of patterns, but not really talking about trends and patterns in space and time, and definitely not usually talking about how we can use it to make decisions in the environment. And so I've been mentioning remote sensing of water quality and sort of training data sets, but what is remote sensing of water quality? Basically this image is showing all the different constituents that can control water quality. I'll zoom in a little. And you have a bunch of stuff that controls the color of the water. So you have like cyanobacteria, sediment, phytoplankton, suspended particulate matter, or total suspended solids if you're a river person. And all of these aggregate to give the water color. And then that water color goes through the atmosphere, is filtered through vapors and clouds and other things, and it finally reaches the satellite. And that's sort of the sensor that we have is the sensor at the satellite or at the airplane. I'll be talking about satellite remote sensing. And so, this is sort of all the complex things that lead to the water quality, to the color of water we see. And you can use different methods to convert this image, this color, into predictions of how much phytoplankton or sediment is there. So more simply, you can just think about this from an image over like Florida. Florida has a huge variation in lake color. So at the bottom left of this image, down here, we have a bunch of lakes that are sort of algae bloom rich. And then up to the right, we have more sedum, DOC, dark lakes. And there's just a large variation in this color. And these images tell us something about the concentration of these constituents in these lakes. And so the way remote sensors talk about this is the inherent optical properties. If a pixel's green, maybe it's going to have more chlorophyll. If it's blue, it's going to maybe be just open water. If it's kind of brownish, it might be color dissolved organic matter. And if it's a bright tan, maybe it's sediments. And so that's just sort of generally how remote sensing works. the real reason that I'm so excited about remote sensing is the sampling density of remote sensing in almost every watershed globally will be far higher if we can turn these images into predictions of constituents than the observations that we have on the ground, the in situ observations. So on the left, this is the Colorado River Basin, the upper Colorado, and on the right is the St. John's River Basin in Florida. The sort of segments of river that are highlighted in bright green have been sampled at least once in the history of the water quality portal. So in the history of sort of the federal government managing water quality data. And then on the left, in the black has never been sampled. So you can see in the Colorado River, it's relatively poorly sampled, whereas the St. John's River is one of the most highly sampled watersheds in the country. But even there, in the St. John's River, remote sensing sees these water bodies orders of magnitude more frequently and more water bodies, both in terms of lakes and streams, depending on what you're observing. And then it's even more pronounced how much more lake observations you get in the Colorado River compared to in situ. So if we can turn these remote sensing data sets into predictions of constituents, we really will like increase our data by hundreds of times. And so we're sort of excited to try to do that. And this is just another way to think about that. This is just the number of overpasses per year from Landsat. So these are these Landsat tiles, and you have increased overpasses where the Landsat overlaps with itself. So that's sort of like over here where the Green River is. The Green River is getting sampled twice as much as this section near Moab, just because it's sort of in between these Landsat scenes. And I'll come back to these figures in a second. And so if we have all these images, how do we turn that into an estimate of water quality? So this is just a figure from a paper that just shows basically, in this case, as you had increased screen reflectance, it was not very predictive of TSS. Increased red reflectance was more predictive. Red edge was much more predictive. And then the near infrared in this case was very predictive of TSS. And so this is just a local empirical approach. And that's a common approach that's been used for a long time in remote sensing, is sort of local empirical. So you go out, you measure a bunch of samples, you either have the satellite or a drone pass over, you make sure you do some local algorithm to figure out, it just as simple as this, near predicts TSS with very high accuracy in this case. But that doesn't work when you scale it up. So to go globally, we know that different basins have different sediment concentrations, different clay content, and that's going to change this relationship a bunch. And so to do it more at a national or global scale, we really need large open access data sets. And so to go from local to global, for work in my postdoc, we built this data set called Aquasat. Allison Appling and a bunch of others were helping with that. Tamlin Pavelski, Simon Top, Zhao Yang, and at the University of Washington, David Buttman and Catherine Kuhn. And this video just sort of shows how we built that. This paper is now published, but basically we took the water quality portal, which has been sort of assembled, and every time something flashes sort of tan or purple here, people were taking samples just randomly out in the field of either chlorophyll A, dissolved organic carbon, total suspended sediment, or Secchi depth. And what we did is we took these samples. You can see that in the 80s there was relatively few, and if we go into the sort of 2010s, one of the peak years of data in the water quality portal, you start to see how much we've been sampling the rivers and lakes of the United States over time. And just to be clear, these are only samples on remotely observable rivers and lakes. So rivers that are wider than 60 meters and lakes that are wider than 60 meters on each side. So this is sort of the in situ data set that we need. So now we have in situ concentrations in these water bodies. But to make it viable with remote sensing, we need to combine it with another open access data set. So this is the launch of Landsat 5. So you see the sort of scenes of Landsat 5 as it takes pictures in the country. And as we walk through this video, I might fast forward a little. You can see that we eventually go through different generations of satellites. This is when we have Landsat 7 and 5 going, and then Landsat 5 drops out. So now this is just Landsat 7. And then eventually Landsat 8 comes online. And that's sort of where we're at now with Landsat 7 and 8. Obviously, we also have Sentinel. We didn't deal with Sentinel data in this approach. But in this case, every time something lights up sort of bright cyan, that means that it was a cloud-free image. And the gaps in the satellite data are just because it's too cloudy to use. And so what we did with this approach is we essentially took this data set and the in situ data set, paired them together so that every time someone took a sample randomly in the field, just for some local water quality monitoring program, and we had a satellite image going over it the day before or the day after or the same day. That went into our database, which we called Aquasat. So now every time something's flashing white, we captured that data and we put it in our data set. And that's what we published as an open access data set to encourage more people to do remote sensing of water quality. And I always hate that you can see my YouTube history. I watch a lot of cooking videos on YouTube. So that's our Aquasat data set. We built that one. It was really focused on chlorophyll A, DOC, Secchi disk depth, and what am I missing? Something else. Total suspended sediment. But Evan Dethier and others, they built another data set that's truly global, covers the Amazon and some other areas, that is focused on sediment, and they have far more sediment samples than we do. So now there's 2 open access data sets for doing remote sensing of water quality. And now I'm just going to walk through some examples of what you can do with this kind of data once you have it. So first we'll talk a little bit about lake clarity. This is work led by Simon Topp and the rest of his group, and Zhao Yang and Claire Griffin and Emily Stanley. This is a Wisconsin party here today. And this is just Simon's using a gradient boosting modeling approach. We're talking with folks, everyone at this conference basically, about shifting to a knowledge-guided machine learning approach, but we've just been using the gradient boosting approach for now. And so this is just his validation metrics for a national model of water clarity. So this is national for the United States, and this is, he gets an R-squared of 0.72 and an RMSE of around 1 meter. So in any given lake, we're fairly confident we're within 1 meter if we have a Landsat image. And this is for this sort of same day, like any given time, but our results get even better if you're interested in sort of the average behavior of a lake. So this is aggregated for average lake summer clarity. So this is Secchi disk depth over the summer. And we have a much tighter fit because we're sort of maybe collapsing some of that noise. And I think we can really improve this approach with some of the kgml stuff we've already talked about. So now that we have this data, we have this model, we can apply it to a bunch of lakes all across the country. So what Simon did is he took the National Lake Assessment data set, and then he took data from 1984 to 2019, and he applied his model and looked at clarity variation in the National Lakes Assessment data, which is sampled once every 5 or 10 years. I can't remember right now. And then he also took a totally random sample of lakes all throughout the country. NLA is supposed to be representative sort of average lakes in these different regions, but we just took another random sample of 20,000 additional lakes. And we have Secchi disk depth for them on average about once a month since 1984. And what we show in this paper, what Simon really shows is that there's a lot of narrative from in situ based data sets on the far right here that water clarity in a lot of places is decreasing. So basically things are getting murkier. And that's sort of what some of the in situ data sets showed on the far right. But if you look at this random sample of lakes or just the lakes that we have in the National Lake Assessment, we actually saw a far more consistent increase in water clarity. So by having so much more lakes that are observed so much more consistently, and in particular small lakes that are not problematic, because if you remember, we're using the water quality portal for a lot of these in situ studies, and the water quality portal data comes from agencies monitoring lakes. Well, which lakes get monitored? The ones that are problematic often. And so if you look at all lakes, essentially a random sampling of all lakes, you see far more consistent trends of increasing clarity, which is sort of surprising, and maybe some evidence that things like the Clean Water Act, in particular in cities, because we see the fastest increases in clarity around cities, maybe they're working a little bit. So this is some results we're just sort of right off the press. This is in review, and Simon Topp led that at UNC Chapel Hill. So that's lake clarity. John Gardner at UNC again is working on riverine sediment, and Zhao Yang is working with us too, and Tamlin Pavelski and Simon as well. And what John has done is take the same approach as Simon. So he has a model, a gradient boosting model again, for rivers all across the country now using Aquasat data. And he's predicting total suspended solids. So how much sediment is in these rivers. And this is a national model again, and we're getting percent error of around 18% and a median error of 12 milligrams per liter and an RMSE of 30. So not bad, given that we're applying this model at once everywhere with relatively little local data. All we're using locally is the elevation of the river. And so we'll sort of just zoom back in on these 2 watersheds. This is the Colorado River. And actually, I'm just going to focus on the Colorado River. and this is where I sort of applied some of John's sediment models, and we can do really cool stuff with these models. So this is just a map of the Colorado River that is in one Landsat tile. And so you get about 200 kilometers of continuous observation from Grand Junction to sort of Lake Powell. And we can see just average TSS here. So as you're going down, of course, and you get the Gunnison River coming in, you pick up some extra sediment. And then you really see this big increase in sediment down river as you hit the Green River, but not for long, because then you go into the sort of slow water moving down here at Lake Powell. So you have this really sort of beautiful image of what is the average conditions of the sediment. But again, with remote sensing, we can do more. We can look at the not just the average conditions, but the sort of conditions at any given time. So when there's a Landsat satellite overhead and it's relatively cloud-free. So this is just the total suspended solid concentrations going from the sort of upstream that we just saw up near Grand Junction all the way down to Lake Powell. And this is just near the max discharge of the Colorado River. And what you can see here is relatively consistent lines where we're basically increasing sediment. You can think of this as snowmelt in this region, where all at once the whole landscape is wet and supplying a bunch of sediment downstream, and it's consistent. As every river comes in, you have a relatively consistent increase. In black is the sort of average condition. And these individual lines are different days, but they sort of mirror the average condition. And that's really different from the mean Q. So now we're at mean Q. We're going to be later in the summer in this region. That's extremely, the hydrology is really driven in the late summer by random patchy thunderstorms. And you get to see that in what I've been calling the spaghetti diagram. So this is sort of just showing the same profile, but we have the sediment profile that's completely different. And you can see different tributaries contribute sediment at different times. And so we're really able to unpack the sort of landscape metrics of what's going on. Is the Green River diluting the Colorado River? Is it adding sediment from these images? And this is sort of just the really early phases of this work. I'm just going to keep going. Riverine DOC, we can do the same thing. This is with Matt Cohen and Jim Jowitz at the University of Florida. So again, same Aquasat basic thing. We're using gradient boosting again. I totally am aware that we should probably try a new model approach. We've compared a bunch. For now, gradient boosting has worked the best. Again, we have pretty low error, 15% error on DOC in the Florida St. John's River. And so again, here we can just see really neat patterns. You have sort of low DOC going in and out of these lakes, which are maybe spring fed. And then Matt tells me that this is a really wetland rich area. And so these brighter yellow areas have higher DOC. And then they go into Lake George, and here you get a lot of spring water coming in, and so it's diluting that DOC. And so you can just see really neat spatial patterns with this data. And spinning these models up, because Aquasat is open access, is actually super fast and easy. And we're trying to publish a lot of the tools to do this so that more people start to use this approach in their assessment of water quality. And again, this could be local or global work that you could do with the same sort of data sets. So that's the DOC. I'm going to just rip through the Algae Dynamics. So basically, we've worked with some folks in France to apply this at a different river. And we've worked in Loire. We don't predict chlorophyll A with a ton of accuracy. The RMSE on this is like, or the error, RMSE error on this is about 80%, so not great. But in general, we actually still see strong trends that are consistent with what in situ data sets show, which is that the Loire River has a decreasing concentration of chlorophyll A and TSS. And then really cool, we can show that basically the reason that is that macrophytes, which used to be stuck in the upper watershed, oh no, it's not playing. That's a GIF. Oh well. Imagine this GIF shifting where the blue in the bottom crawls upstream. So macrophytes are essentially crawling downstream and choking off sediment and chlorophyll A. And so even though the primary productivity in the system is the same, it's actually shifted from being basically mostly pelagic algae to macrophyte dominated. And I'm gonna say future work real quick. We know we're gonna use kgml, PGDL. We're trying to do some transfer learning. This is in red is remote sensing, or in red is in situ observations of Secchi disk depth in a lake in Honduras based on predictions from our national US model, subsetted to lakes that have similar color. And we're sort of trying to do this. I think I'm going to try to talk to Jared about how to do it more intelligently. And yeah, we want to integrate lake, river, and coastal approaches. And I'll just sort of stop there. I think I would like to have maybe one question.
That was fantastic. And there actually are a handful of questions. Just to let everyone know, we have a break scheduled from 3 to 3:10, but I'm going to probably let Matt's questions bleed a little bit into that, just a heads up. So Matt, in no particular order on these questions, can you talk specifically about the software or code and processing platform that you use?
Yeah.
Is it cloud-based?
This is cool. This is, we developed this with Allison and Simon, and basically all of this is done in R and occasionally our markdown calling Python. So this is Google Earth Engine. And for those, if there's any remote sensors in the audience, we're using surface reflectance from the USGS. So we're not processing the imagery with any specific atmospheric correction or anything. We're just using what's out there already to sort of increase the scale at which we can do this. So yeah, it's mostly local, and then it's cloud-based sort of when we grab imagery.
Nice. Have you tried to perform any predictions ahead of time? For example, forecasting color of water from some other kind of covariates?
Yeah, that's a great idea. I've written a lot of proposals to do that, but none of them have gotten funded. We want to do that. I think that's where the kgml approach is vital. Frankly, our approach is agnostic to mechanism at all. So we shove just whatever data we can to get a reasonable prediction that works well on validation and test data sets. And so there's zero process. And so I think if you're thinking along the lines of like Kaylin Carey's work and others where you would want to predict maybe a week or two ahead about overturn or if there's going to be a bloom, I think our data could drive models that use our data to sort of do something more like what the previous talks were about. But right now I wouldn't use our data to predict forward.
Great. Do you take into account any spatial dependence, or is the analysis conducted considering just a given pixel in time?
Yeah, it's mostly pixel level, and again, that's a fantastic idea. And for river lake continuum, we just submitted a proposal to do exactly this, because obviously, like Allison's talk, having a network aware prediction is clearly the best way to sort of get network scale predictions, because you want to be able to say like, hey, if sediment is 7 in this reach and there's no incoming tributary or anything, it should probably be something around 7 in the next reach. And we don't do that now, and it's a clear point of improvement, just like it would be a very clear point of improvement to include some reasonable process knowledge, like, hey, it definitely rained in this basin, so it probably is going to increase sediment and things like that.
Yeah. And so the last question is sort of a dual question. Could new remote sensing data be used as additional drivers, which can be helpful in a kgml setting? For example, if clarity was available as a continuous variable rather than a fixed parameter, could that improve your models?
Yeah, that's exactly what I have talked to Jordan and Allison about doing, where we would maybe use Simon's clarity output to help drive some of their temperature models, for example. Or in Jared's talk, I was thinking, well, if he knew the sort of color variation, not just psychodist depth once, but like, probably once a month, and we could think about like matching profiles based on their variation in color, I think it could drive these more kgml models. I think they can like feed to each other. We could get better predictions using remote sensing, and I think the kgml models would do well to use it. And you could just use the raw imagery even in the kgml, because it would sort of figure out the relationship. So anyways, that we've been having those conversations, but so far haven't done it. And I'm really excited to work on that front. So if anyone wants to, please email me.
And my personal question following on that is, are there new satellites coming online that could vastly improve some of the like potential water quality variables?
Yeah, so Landsat 8 and Sentinel-2 are already far better than 5 and 7. So big upgrade by having this ultra blue band. And then there's actually a development. It's always funny talking about satellites. There's a development team working on a satellite that's launching in 2027. So, for the young in the crowd, we can still get on that one. And that's an inland water quality satellite. So it is built for our community. I don't know a ton about it because it's in this like engineering phase, but that's one thing. And then a pitch that I'm constantly making is that when SWAT launches, which will sort of, the promise of SWAT is global estimates of discharge for every river bigger than 90 meters, and global lake height, therefore global lake volume for every lake larger than 250 meters on a side. To me, that has to be paired with water quality estimates. So Landsat 9 and Landsat 8 and Sentinel-2 sister really well with other satellite missions that are about to launch. So that's like SWAT and then NISAR too. So there's a bunch of things that I think, I'm not from this community. I did my PhD in totally other things that it's very exciting to think about how we can use it, but it's actually very hard. It's a big barrier. And our group is really trying to lower that barrier to make doing these kinds of, oh, I want to know what Colorado River sediment is, and just making that like a couple days instead of like a whole PhD.
Excellent. Well, I think we all appreciate that.